Hello. So today what we will be doing, hopefully, is deriving the Navier-Stokes equations, which pretty big task. Anyway, I'm gonna have a go. I made notes as per usual, and hopefully this won't go on for too long. It is probably one of the largest things I've attempted on this channel, but it's okay. Anyway, I'm going to get right into it. So we're going to start off with a Newtonian fluid, and we're going to assume it's in a continuum and basically just spam F equals ma. So what we can start off with is if we have a particle in our field u, which is a function of x, t, where x is some position vector or some coordinates x, y, z, and this is our velocity field, and the acceleration here is going to be a. So a is of course just the derivative of that, but this is a field. So we can say that this is d dt of u of x of t, y of t, z of t, t. It's quite a big thing. Now we can use our multivariable chain rule, which anyone who's done Calc 3/multivariable will know. So u t plus u delta x dx dt plus du dy dt plus u z gz dt, and this is just taking the chain rule of each of the parts of this, I guess you could say. And of course dx dt, these are just going to be u sub x, and this one is u sub y, and this one is u sub z. So then we can say that this is the time derivative of our fields plus u sub x times the x position derivative of our fields plus u sub y of the y derivative of the velocity field plus u sub z of the z derivative of the field. Cool. Now we can use a shorthand notation for this, because this is just the gradient times by the field. So we can write this as this c plus u that's the same thing, and so we denote this with a thing called the material derivative operator, which is d dt, and our function here is just u, which is du dt. That is just a capital D. Anyway, now if we use Newton's second law here, rather than F equals ma, because this is for various reasons, we're going to use the original Newtonian definition, which says that if we have our total force F t, that's equal to the time derivative of this function p of t, which P of t is just our total momentum, which is the integral, that's not an integral over v of rho u dv. Yeah, that's right. Cool. So that would be a volumetric integral. Now we differentiate the integral because obviously we want to find a value for this. Now we can use something called the Reynolds transport theorem here to look at this section. So we start off with, or I'll just write it out first of all. V A. This is just a quantity A that we're integrating and differentiating over and with respect to. And the Reynolds transport theorem says that this is over V, the integral of the of this. That should be plus, sorry. Plus del A cross U, but like, yeah, dv, and we can just sub in the A here is equal to rho u, obviously, because that's what we've got up there. So we get that dp, yeah, sorry, momentum is a vector, I should have put a dt equal to the volumetric integral of that rho u over with respect to time plus rho u cross u dv. And now what we want to do is expand this divergence term specifically. So I'm going to take that part out. And we can say that nabla or del dot rho u cross u. We're going to do Einstein summation here, so I'm going to put this over the ith component, and that will be the position derivative, yeah, j rho ui uj, which is just ui because that's irrelevant, xj rho, that's not, none of these are very good rows, uj plus rho uj partial ui over partial xj. Yeah, that's correct. And now again we want to look at what this means for our vector notation. So the first section can be notated as u times the divergence of rho u, and the second part can be notated as the density rho times u dot nabla u. There. And so if we substitute this all back into our equation from or rather if we substitute all of this into here, we get that the divergence of rho u cross u is equal to u, I'm going to use these brackets, plus rho u dot del u. Cool. Cool. Wunderbar. So now we want to put this back into here, and do some term splitting or parting. But this is going to make quite a big messy integral-y thing, which is going to be a running theme in this video. So we can chalk this down to this integral over v of a big bracket. Now this might look somewhat familiar because it's just subbing in what we've already found. U t, that should be in its own bracket as well, plus u, and then what we got above, u plus rho u dot del u dv. Okay, that's our general momentum here, or rather our total momentum, not general. General wouldn't be wrong to say. It's not specific, but no, total momentum is more correct. No, it would be the total momentum. Sorry. Anyway, now we can pull things out and group terms inside of the integral. So we can say this integral over v of u times rho dt plus del rho u, don't forget that, plus rho. So we have a term in terms of rho and a term in terms of u, and inside of those we have some partial differentially thingies terms. Nice. And these mean things. So we have two terms here. We have these two separate parts. So this is the continuity equation, which is kind of just conservation mass. And what this says, or at least what we know, or if you look at the inside, we know that partial rho partial t plus the divergence of rho times the velocities is equal to 0. So that whole term goes to 0, which is quite beautiful. And this term should spark some interest because it's the material derivative from up here. So what we're getting at is that that's 0, and that's just rho du dt. And so we can say then that this is equal to the integral over v of rho du dt dv. Lots of d's. Anyway, the next thing we're going to do is look at the forces that are acting on our fluid. And so we've got two forces here. We've got our body forces, which what we're going to do is equate these at some point. Ft is equal to the volumetric integral of rho g dv, and that's our gravitationalness plus the line integral over, or rather the surface integral of the forces acting on the surface. So here we have our stress sigma times n, which is just, actually these are both vectors, which is just our normal vector here, ds over our surface. And this is kind of useful because we have a useful formula for getting rid of annoying things like this and making them over volumes. Pardon me, excuse me, whatever you say when you're coughing. Anyway, we're gonna do the A thing again. So for a field A, we have that the volumetric, or rather, I'll write it the other way around. over S of A dot N ds is equal to the volume integral of nabla, or rather the divergence. Why am I writing my A's like that? I do this a lot and it really annoys me. I'll be writing like delta and then an A afterwards, or what's the one that, because obviously I'm still doing A level, so I keep having to. Recently we were actually doing some Young's modulus, and it's E is equal to F delta L. No, FL over A. See, I'm doing it now. A delta L, and I always do like delta delta L, or I'll write like A and then A again and L. It's just a mess. It's just honestly a mess. I think we should just outlaw one of them, get rid of one, and keep the other one. Anyway, that was my tangent. That's useful because that's the exact form we have there. So we can just sub in that our total force F of t is equal to, I'm just going to write one here, rho g, because obviously we can put them together, plus the divergence of our stress tensor. This is the tensor divergence. Did I say that it was a tensor earlier? The stress is not a vector, it's a tensor. Yeah. That's not very good, whatever that was. I'm going to continue generating it with the arrow on top, even though it's not a vector. I'm really sorry. Hope that doesn't anger anyone greatly. I'll put that in brackets just for neatness. Now we can equate these two, and hopefully by the end of this couple of bits we'll have the Cauchy momentum equation. But the integral of over v of rho du dt dv is equal to that rho g plus divergence of that dv. Subtract them onto one side. V of, and we can pull out the rows, but I don't need to. I'm not going to. Rho du dt minus rho g minus that dv is equal to 0. And the only way for that to be true is for the integrand to be true. Thus, rho, or rather that implies that rho du dt minus rho g minus the tensor divergence of the stress is equal to 0, and so we end up with the Cauchy momentum equation, which is that the momentum times the material, or rather just the, that's kind of just the material acceleration, is equal to the divergence of the stress plus the gravity. That's not, I'm still not happy with that rho. That's better. Rho g. That's our first box for today. Well done. You've made it 20 minutes in this video, and we've only got another page and a bit of notes. So that's good. The next thing is, oh yes, tensory bits and bobs. Right, there's going to be a lot of subscripts, so lock in. We can decompose our tensor into a thermodynamic pressure part minus pi, and that I should make clear that's a p, not a rho. and a viscous deviatoric part, which is going to be tau. And we can say that this sub ij is equal to minus p, and I'm going to do my horrible delta thing. I was planning on doing this video on a derivation of the principle of least action from the Feynman path integral formulation, and I'm sure people would have been very sick of my deltas after some time. And then the torque, no, not torque, the viscous deviatoric part. I'm just going to call it tau, because I'm not saying viscous deviatoric part every time. Am I saying that right? Deviator, because it's deviating, yeah. Some tau. Anyway, there's a useful rule for Newtonian fluids, which is that the viscous stress is linearly proportional to the rate of strain, and our rate of strain tensor is E sub ij. I keep writing j's instead of i's, which is a half, and I'm going to use some nice Einstein-y notation here, plus the I derivative. That should have been the j. Yeah, that is the j derivative of uj. And if we take the most general isotropic rank 4 tensor relationship, we get here that tau of ij equals to mu e ij plus lambda delta ij times the divergence of our fields. And we can substitute the ej into there, which is just going to be the halves cancel out, so it is mu times, and I'm going to write this out in full now, just for the sake of completeness, j plus uj over xi plus that times that j derivative of uk over derivative of xk, and that's just a different way of writing our divergence there. And what we want to do a bit further to be honest, I mean, we don't even need a box around that, I realise now. I'm going to get rid of that. You're not so cool, Mr. Coach. I mean, it's still pretty cool, but it's not that cool. We'll keep going. We'll press on. Sorry. The next thing we need to do is find the divergence of the tensor for the momentum equation. So in index notation, the ith component is the jth partial. So we can write that out fully and say that the derivative with respect to x sub j is equal to minus dp dx plus d tau j dxj. That'll do. And we can differentiate this to find that with respect to xj. And now this is going to be a mess of partials, so I'm really sorry about that in advance. Of ij is equal to partial xj of that, which is mu times I over partial xj plus partial uj over partial xi plus lambda delta ij duk dx. Okay, I've completely dropped all of the... So, well, no, I shouldn't need them because I'm giving specific components here. And carrying this out, which is just fairly basic calculus because we're not really doing too much, to be honest, is the second partial derivative with respect to xi first and then xj. I can't remember if that's commutative, but I'm going to err on the side of caution. Mu times the x partial of this over xj plus lambda times, oh no, I don't want to run out of space, natural xj times that ij partial uk with respect to xk. Okay, it fits. Now this again is a bit of a messy thing, but we can make sense of these terms. So this is simply the Laplacian, which is del squared u sub I. The second term, as we've seen before, just that section without the mu's, is the divergence of u, and looking at the final term, because it is, due to this delta ij, the derivative only acts when j and I equal. Excuse me. And so this just becomes the xith derivative of the divergence. So that's I of that. That is, yeah. Okay, good. That seems right. And so now we can say that, because this is just the same thing as what I wrote above, that is equal to mu Laplacian of u sub I plus mu plus lambda in the bracket xi del dot u. Cool. And I can get rid of things and just make them all general, because this applies to all of the indices, which was the idea of using that scary Einstein notation, which is not scary and is very cool. Is equal to mu del squared u plus mu lambda del dot u. And now what we can do, because everything is in terms of u instead of scary stress and things, what was it? Oh, I'm making lines all over the place. Where's scary stress and things? We came to a nice little conclusion, somewhere around there, before all of that happened. Anyway, we can sub it back into Cauchy's equation, from before, the one that I boxed and then I unboxed because I wasn't happy with it being in a box. I didn't like that. I think it should be free. U is minus delta p minus del p plus mu Laplacian of u plus mu plus lambda nab del dot u plus rho g. Okay, there's enough space for everything. Now Stokes assumed that bulk viscosity is 0, which is a fair hypothesis because you know often it is kind of useful, and in that circumstance, or rather that implies that 3 lambda plus 2 mu is equal to 0 just by comparison of coefficients. But and that would mean that lambda is minus 2/3 mu, and that would make it solvable. But that's kind of irrelevant for incompressible fluids, which is what we're really interested in here. So remembering our definition of we didn't actually define that as part of a Newtonian field, but what we're going to say, give or take with some sleight of hand, is that the density is constant, because that's what incompressible is. The continuity equation becomes quite simple. It just equals out to 0 essentially. And what we end up with is that this term kind of goes away, and then we can divide the rho out of everything else. I think. Lots of oh yeah, because we have to then. Oh yeah, and we can just define kinematic viscosity, which is our nu, which I can't really draw, but it's gonna look like a weird V thing. That'll do. Is equal to mu over rho. We can sub that in, and we end up with our standard form, which is the time derivative of the velocity field plus the velocity dot del times the velocity field is equal to minus 1 over rho delta p plus nu, or rather our kinematic viscosity, times the Laplacian times our field. I'm not happy with how this is set out. Squared times u plus g. And that can definitely go in a box, because that really is the standard form of the Navier-Stokes equation for an incompressible fluid, which is quite useful. Yeah, I mean, this equation is our most advanced understanding of how fluids behave, really. So it's pretty cool that you can get to it by kind of just F equals dp dt. But regardless, I really enjoyed doing that, even though it was quite long and a bit scary at times. I think I made sense of it in the end, and we did end up with the standard form. And I did follow my notes, so I'm quite happy, and I hope you all are too. And I hope you have a very nice week. I will see you next week. Goodbye.